Welcome back to Basic Electronics. In this lecture, we will illustrate how a Bode plot can be constructed using contributions from the various terms in the transfer function and then adding them together. We will apply this procedure to an example. Finally, we will compare the results of the Bode approximation with the actual magnitude and phase plots. Okay, let us begin.
So we have looked at how to get magnitude or phase plots for various terms such as a zero or a pole or a constant s, s squared, etc. Let us now consider a transfer function which is a product of two transfer functions, and let us see how to obtain the magnitude and phase plots knowing the behavior of h1 and h2 individually. So that is the problem we are looking at. Okay, let's consider the magnitude first. The magnitude of h is mod of h1 times mod of h2. Let us now take log of this and multiply by 20. So we get 20 log h is 20 log h1 plus 20 log h2. What is 20 log h1? It is nothing but h1 in dB. What is 20 log h2? Is nothing but h2 in dB. So at any frequency, to get the net h in dB, all we need to do is to add these individual contributions. So in the Bode magnitude plot for h, the contributions due to h1 and h2 simply get added. So that's very simple. Let's look at the phase now. h1 of j omega and h2 of j omega are complex numbers, as we have seen before. Now at a given omega, let h1 be k1 angle alpha, which is the same as k1 e raised to j alpha, and let h2 be k2 angle beta, that is k2 e raised to j beta. Here k1 and k2 are some real positive numbers. What about the angle of h now? The angle of h is the same as the angle of h1 times h2, that is k1 times k2 e raised to j alpha plus beta. That is what we get by multiplying this expression by this expression here. In other words, h1 h2 has an angle of alpha plus beta. That is, the angle of h is simply the angle of h1, which is alpha, plus the angle of h2, which is beta. So that's also very simple. So in the Bode phase plot, the contributions due to h1 and h2 at any given frequency also get added. And the same reasoning in fact applies to more than two terms as well. And that is the nice thing about Bode plots. It makes it very easy to plot functions where we know the individual contributions. Okay, let us now apply the method that we have learnt in the last slide to this specific transfer function. 10s divided by 1 plus s by 100 times 1 plus s by 10 raised to 5. Now this function can be written as a product of four functions, h1, h2, h3, h4. h1 is 10, h2 is s, h3 is this pole 10 raised to 2. So it can be written as 1 over 1 plus s by p1, where p1 is 10 raised to 2 radian per second. h4 is this other pole, 1 over 1 plus s by p2, where p2 is 10 raised to 5 radians per second. And we have learnt how to plot the magnitude and phase graphs for each one of these. So we can now plot the magnitude and phase of h1, h2, h3, h4 individually versus omega, and then simply add them to obtain the magnitude and phase Bode plots. Okay, let's look at the magnitude plot first. So we're going to plot mod h in dB versus frequency on a log scale, and the frequency is in radians per second. Let's start with the first function h1, which is just a constant. So the magnitude of this is independent of frequency, and in terms of dB it is 20 times log of 10. So that is 20 times 1, or 20, that is 20 dB constant irrespective of frequency. Okay, next let us take h2, which is equal to s, and we have looked at this function before. So how do we plot this? We know that at omega equal to 1 the magnitude of h2 is 1, which is 0 dB. That is this point here, omega equal to 1 or 10 raised to 0, and h is 0 dB. So we know that the graph will go through this particular point, and we also know that h2 will increase as omega increases, and we know that it will do that with a slope of 20 dB per decade. So all we need to do now is to draw this straight line with a slope of 20 dB per decade. So as we go 1 decade in frequency, we go 20 dB in mod h. Let us consider this h3 of s now, which corresponds to a pole. The pole is at minus 10 raised to 2 radians per second, and we have seen how to deal with such a term. We have two asymptotes, a low frequency asymptote h equal to 0 dB up to omega equal to p. P in this case is 10 raised to 2 radians per second, and then a high frequency asymptote with a slope of minus 20 dB per decade. And both of these asymptotes meet at this common point, that is omega equal to p, which is 10 raised to 2 radians per second, and h equal to 0 dB. The next function h4 of s is very similar to this h3 of s. The only difference is that the pole is now at minus 10 raised to 5 radians per second. So for frequencies less than 10 raised to 5 radians per second, we have this low frequency asymptote, that is h equal to 0 dB, and for higher frequencies we have the high frequency asymptote here, which has a slope of minus 20 dB per decade. And now we have all the components of h, which, if you remember, is h1 times h2 times h3 times h4. And now we can add all of these plots to get our net magnitude versus frequency Bode plot. Where do we begin? Let's begin at 10 raised to 0, that is omega equal to 1 radian per second, and see what the various values are. This is 20 dB, this is 0 dB, this is 0 dB, this is also 0 dB. So when we add these four values, we get 20 dB. So that is our starting point. Omega equal to 10 raised to 0 radians per second, mod h equal to 20 dB. Right there. Alright. What happens after this? After this, our first breakpoint is this one at 10 raised to 2. So what is the situation between these two frequencies? This is constant, slope 0. This is constant, slope 0. This has a slope of 20 dB per decade, and this is constant with slope 0. So the net slope is going to be the sum of all these slopes, which is in this case the same as this slope, that is 20 dB per decade. So therefore up to 10 raised to 2, up to this pole, that situation is going to prevail. So we draw a straight line with a slope of 20 dB per decade. and we stop at this point, because now things are going to change, because this h3 is going to change. What happens beyond 10 raised to 2 radians per second? What is our next breakpoint or corner point? This function does not have any breakpoints. This one also does not have any breakpoints after 10 raised to 2. This one also keeps going, it does not have any breakpoint. So the next breakpoint is supplied by h4, and that is right here, 10 raised to 5 radians per second. So now we take the range between our present breakpoint, which is 10 raised to 2, and the next breakpoint, which is 10 raised to 5. Alright, so now in this range, let us find what the net slope of our magnitude Bode plot should be. This one has a constant slope, 0 dB per decade. This is minus 20 dB per decade. This is plus 20 dB per decade. And this is 0 dB per decade. So the net slope is 0, minus 20, plus 20, plus 0. So that is a net slope of 0 dB per decade. And that is why we draw a straight line with a slope of 0 dB per decade, and we stop at this breakpoint, which is the same as this pole here. After this breakpoint, there is no further breakpoint to worry about. So all we need to do now is to find the net slope for omega greater than 10 raised to 5 radian per second. This is 0 dB per decade, minus 20 dB per decade, plus 20 dB per decade, and minus 20 dB per decade. So the net slope is 0, minus 20, plus 20, minus 20. That is a net slope of minus 20 dB per decade. So that is what we do. From this point, we draw a straight line with a slope of minus 20 dB per decade. And that completes our magnitude Bode plot. Let us make a comment on some practical matters. We note that this y-axis is from 0 dB to 80 dB. And the question you should be asking at this point is, how did we know that it should go from 0 dB to 80 dB? Let's say that the frequency range is known. Given this frequency range, how did we know that our h of s is only going to vary between 0 dB and 80 dB? The answer is we did not know. It is in fact not possible to know in advance. And there is some trial and error involved in these matters. So we know the starting point, but we don't know what shape h of s is going to take, whether it's going to exceed 80 dB, whether it's going to fall below 0 dB, that we don't know in advance. And therefore it's a very good idea at this point to work out some examples from some textbooks and get a lot of practice in these matters. Okay, let us now compare our Bode magnitude plot, this one, with the exact result for h of s. And how do we obtain this exact curve given here in blue? What we do is start at some omega, let's say this value, substitute that in this expression, find mod of h. That gives us one data point. Then we go to another data point and so on. And after we get sufficient number of points, we join those. So that is how this exact magnitude plot is obtained. One can of course write a computer program to do that, and you are definitely encouraged to do that. It's fairly straightforward. Write a C program, not some higher level program like MATLAB and so on. You will learn much more if you write a C program. Alright, So how does the approximation compare with the exact result? It compares pretty well, and definitely away from the poles or away from the corner points, the agreement is perfect, and even in between we have an excellent idea of what our magnitude plot is going to look like. Let us now look at the phase Bode plot, and we start with h1, which is equal to 10. This is a real positive number, so the phase is 0 degrees irrespective of omega. Alright, next function is h2, and that is equal to s, and as we have seen before, the phase of h2 is pi by 2 because s is equal to j omega, and that again is independent of the frequency, so that is 90 degrees for all frequencies. Next, let us take h3. This represents a pole, and if you remember, what we do now is locate the pole, that is here 10 raised to 2, go 1 decade below that frequency, so we come to 10 raised to 1, and for frequencies less than that we have 0 degrees. Then we go 1 decade higher than the pole, that is 10 raised to 2, that brings us here, and then we draw a straight line, horizontal straight line at minus 90 degrees, and then we just join these two. That is how we get the phase of h3 as a function of frequency. What about h4? It's very similar to h3, only the pole is different, 10 raised to 2 here, 10 raised to 5 here. So the graph is going to look very similar to this graph here, except that it will be shifted with 10 raised to 5 radians per second as the pole. Alright, we now have the individual contributions h1, h2, h3, h4, and now it is a matter of adding them up to get our net phase versus frequency plot. Let us begin at this point, 10 raised to 0 radians per second. What is the phase? Here 0 degrees, 0 degrees, 90 degrees, 0 degrees. So the overall phase is going to be 90 degrees. So that gives us our first data point right there. So omega is equal to 10 raised to 0 radians per second, phase equal to 90 degrees. What is our first breakpoint after this data point? Let us look at these individual contributions. No breakpoint or corner point here. No corner point here. Here the first corner point is at 10 raised to 1 radians per second, and here it is at 10 raised to 4 radians per second. So this is our first corner point. So now we need to focus our attention on this interval between 10 raised to 0 and 10 raised to 1. So let's look at each of these plots again. In this interval, this slope is 0, this slope is 0, this slope is 0, this slope is also 0. So the net slope of our phase plot is going to be 0, and that is what we do here. We draw a constant horizontal line with a slope of 0 degrees per decade. What about the next corner point? That comes from this plot, again 10 raised to 3 radians per second. This is still far away, and now we need to focus our attention in this range between 10 raised to 1 and 10 raised to 3. 0 slope here, 0 slope here, 0 slope here, and this one has a slope of minus 45 degrees per decade. If we go up in frequency by 1 decade, we go down in phase by minus 45 degrees. So this is the slope that applies to our net phase plot, and that is what we do here. We start at this point, draw a straight line with a slope of minus 45 degrees per decade up to our next breakpoint, that is 10⁻³ radians per second. The next breakpoint is this one, 10⁻⁴ radians per second. So let us now calculate the net slope between 10⁻³ and 10⁻⁴ radians per second. 0 slope, 0 slope, 0 slope, 0 slope. So the net slope is going to be 0. So we then draw this line segment. What about the next corner frequency? That is 10⁻⁶ radians per second. And the slope between these two frequencies needs to be computed now, between 10⁻⁴ and 10⁻⁶. And these other three functions have 0 slope in that range. So therefore the net slope is going to be the same as this slope, which is minus 45 degrees per decade. So we then get this segment. And beyond this point, what happens? The net slope is 0 for all of these transfer functions, and therefore the overall slope is also 0. And that completes our phase Bode plot. Here is a comparison between the Bode approximation, the red one, and the exact phase curve, the blue one. And once again, we see that the Bode approximation is an excellent first step towards understanding the behavior of a transfer function. Let us now look at a sequel example of computing the transfer function. This element is called filter Z1 P1. That means it has 1, 0 and 1 pole, and this block is also the same, filter Z1 P1. And the net transfer function from the source to the output is the product of this transfer function and this transfer function. So that is 2 zeros and 2 poles altogether. And these parameters here specify what that transfer function is for each of these blocks. And what is A0, A1, B0, B1? Let us see the documentation for this element. So the transfer function for each of these blocks looks like this: A0 plus A1s divided by B0 plus B1s. So those parameters that we saw correspond to these parameters here. Alright. Also there is a flag called flag asymptote. If we want the Bode plots for magnitude or phase, then we set this flag to 1. And if we want the normal plots, that is the exact magnitude or phase, then we set it to 0. And this specific example is taken from this book here, Signal Processing and Linear Systems by Professor Lathi. And there are several other examples which you should look at and maybe work out some of them. Let us now look at the results. Alright, so here is the magnitude plot. This one is the Bode approximation, and the other one, the smoother one, is the exact magnitude plot. This of course is a log axis. This is also a logarithmic axis. These numbers are actual gain and not dB, but since the scale is logarithmic, the shape of this plot is what we would expect. if we plot dB versus log f. This is the phase plot here. The Bode approximation is given by this curve here, which is a combination of several line segments, as we have seen. And the smoother curve, this one, is the exact phase curve. And this is a very good example for you to practice. So take down all these details, the A0, A1, B0, B1 parameters for each of these elements. Work out what the magnitude Bode approximation should look like, also the phase Bode approximation, and check whether you are actually getting these results or not. The circuit file is right here, test_filter_5.
To summarize, we have seen how to construct the Bode plot of a given transfer function by treating the various terms in the transfer function one at a time and then adding the individual contributions. Bode approximations are useful for understanding transfer functions of filters and also for estimating stability properties of amplifiers, which you may study in a subsequent class on analog circuits. In the next class, we will look at op-amp filters. Until then, goodbye.